All right, this is section 2.9, video 3. So we've talked about the idea of linear approximations. Now we're going to talk about the concept of what's called a differential. Now, you might think to yourself, well, that kind of sounds like derivative or something like that, and it is. It's very similar because you have to use the derivative idea. So a differential, we're going to put on here a graph so I can kind of give you what the concept is. So let's just say we have that curve, okay? And on the curve, right here is a known value. So at that specific x value, there's a known value. And we can draw a tangent line to that curve. So this is where the idea of the linear approximation comes in. So let's draw that tangent line to that curve. Okay. We should be able to agree that the notation dy over dx is the same thing as f prime of x. They mean the same thing. So that's where this statement comes in right here. They are equal statements. Therefore, if I wanted to solve for dy, I would just multiply both sides by dx. dy technically is the change of y, but it's the infinitesimally small change of y, where dx is the really, really super small change in x. Okay, for purposes of our graph here, we're going to represent this change in a slightly bigger fashion so that you can actually see it, but we're really talking about a very small change overall. All right, so we've got our point x. If we want to go to another point and use some kind of an approximation, maybe our point is right here in orange. Okay, that's going to have some kind of a different x value right here. If I want to go from one x value to another x value, there's going to be some kind of a change in x. Therefore, the orange point is going to start with x, but we're going to add delta x to get to it. So this point, this x value right here, is going to be x plus delta x. Okay, so what you should be able to see is that there is some kind of a horizontal change of x that goes in that direction. Okay, there's also going to be from the blue point up to the orange point, there's going to be a vertical change. The vertical change, it would be this distance right here in red. That is going to be a change in y. It's an actual change in y. It's the change of y on the function. However, if we were to use the tangent line approximation, the tangent line approximation is actually going to be up here. That would be the y value that's associated with the tangent line based upon the x plus delta x value. Well, there's an actual change from our blue point up to that red point as well. So from here, from the blue point up to the x point, that change is what is called dy. That is what is known as the differential. So it's actually a change in the approximated x value. I'm sorry, the approximated y value from the function to the tangent line approximation. So that's the dy. The delta y goes from the actual point on the function to the other point on the function, whereas dy goes from the first point on the function in blue up to the tangent line approximation point in red. So that's the concept of what dy actually is. So down here, we're going to state that delta y is the actual change in the y values of the function. Okay, as you see here, delta y is the actual change in the y values on the function right here. That's delta y. dy is the change in the y values on the tangent line, and it gives an approximation for the change in y. It's not exact, but it gives an approximation. Now remember, this is blown up quite a bit, but as this gets really, really, really super small, like right here, if I was to put a red dot right here, that change in the tangent line and the change in the actual function are not going to be all that different. So the closer and closer and closer we are to this x value, the better off this is going to be. And one thing you should also note is that while delta x is the actual change in x, because that's this distance right here, delta x is the actual change in x. Scroll back up. The actual change in the x value from here to here. It's also the dx is going to be the actual change in x as well. So from here over to here is the same thing as if I were to go all the way up here and go from here over to here. It's the same distance. So it doesn't matter if I'm going to the tangent line or to the actual function. Dx and delta x are the same. And that's what this is saying. Dx is the change in the x values on the tangent line, but they happen to be the same. Dx and delta x are the same because the horizontal distance doesn't change. It's just the vertical distance in the function or the tangent line approximation. All right, that's the concept behind it. Doing it is actually pretty simple. All right, so what we want to do is we want to compare the values of delta y and dy if we're given the function that you see there, and the x values change from 2 to 2.05. So the first thing we're going to do is we're going to calculate delta y, which is the actual change in the function. Well, to figure out the actual change in the function, you need to figure out what the function's values are at 2 and 2.05. So we need to do f of 2.0, oops, not 0.205, 2.05, and we have to subtract f of 2. And that'll tell us the actual difference in y. So if we plug in 2.05, because that's not something that I would assume that you would do without a calculator, you're going to get approximately 9.717625. I'm pretty sure that actually terminates right there too. So that's the actual value of the function at 2.05. At 2 works out a little nicer. It's 9. If we plug in 2, we get out 9. So the actual delta y here is going to be 0.717625, just subtracting those two values. That's the actual change in the function. When x goes from 2 to 2.05, the y values change by 0.717625. Now let's see what the approximation is for dy. Well, dy is f prime of x times delta x. So basically what that's saying is I need to go to my function and I need to figure out what f prime of x is, because I'm going to need that. F prime of x. So the derivative of our function is 3x squared plus 2x minus 2. Okay, so my dy is going to be, now I do need to evaluate it at the known value, at the one that's the easy one, the 2. In this case, that's kind of the starting point. That would be that blue point in the graph that was on the previous page. So I need to evaluate, in this case, I'm going to do f prime at 2. And if I plug 2 in there to my derivative, I believe we get, let's see, 8 plus 4 is 12, minus 4 is back to 8, plus 1 more is 9. That makes sense. Of course, that makes sense if I actually plugged it into the right function. I just did f of 2, not f prime of 2. F prime of 2, plugging 2 into the derivative. That's going to be, what's that, 4 times 3 is 12, plus 4 more is 16, minus 12 is 14. So we get f prime of 2 is 14. Okay, that makes much more sense. So we get f prime, which is 14, times dx. dx is the change of x. Well, x changes from 2 to 2.05. So my change is 0.05. And, excuse me, if I multiply 14 times 0.05, 14 times 0.5 would be half of that, which is 7, but I've got one extra 0, so it's really going to be 0.7. As you can see, that's a relatively close approximation. Okay, the actual change is 0.717625. The dy approximation is 0.7. They're close. They're not extremely close, but at least the first decimal is the same. Okay, let's try another one. Now we're going to make a change from 2 to 2.01. So what you should be able to see is that we're letting that second value get closer now to 2 than the first one was. The first one was from 2 to 2.05. This is from 2 to 2.01. We should expect our approximation to be better because it's moved closer to 2. Let's see if that works out. So again, we have to do f of 2, keep putting the decimal first, 2.01 minus f of 2. That's the actual change in y. F of 2.01 using the calculator is going to give you 9.140701. And then f of 2 is 9. So we end up with 0.140701. That's the actual change in y. To do dy, fortunately, we've already taken the derivative. We've already plugged in 2, so we do know that f prime at 2 is going to be 14. This time, the change is 0.01. Multiplying 14 times 0.01 is 0.14. So that is a slightly closer approximation than the one above, because this one is accurate to 2 decimal places. Technically, it'd be kind of accurate to the 3rd decimal place if we counted the 0. So what you should notice is that delta y is going to be approximately dy as the delta x becomes small. So the smaller we make that difference in x's, the closer and closer the approximation to the delta y that dy will be. And one other thing you should be able to realize is that dy is actually easier to compute than delta y, because we could actually do the dy stuff without a calculator. The other ones, you needed a calculator to be able to plug some stuff in. Well, you didn't have to have one, but it sure does make it a lot easier. Okay. So one use for differentials is estimating the error that occurs because of approximate measures, meaning that we are humans, we measure things. We can have errors in measurement. Also, if you think about things on a really grand scale, like a massive scale, a lot of times like astronomers and not even necessarily astronomers, but people who measure like land masses like mountains and stuff like that, they don't physically take a measuring tape or a ruler and measure the height of a mountain. They have to use some kind of mathematical, probably a lot of trig, to be honest with you, to measure like heights of mountains and widths and girths of mountains and stuff like that. Same general idea. So when you're making those measurements, you're going to have error. That's where differentials can be a big help. So let's see what that looks like. It says the radius of a sphere was measured to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. It doesn't sound like that's a big difference in error. What is the maximum error using this value of the radius to compute the volume of the sphere? So again, it's a big sphere. It's got 21 centimeters sphere, but there's a possible error in measurement. Maybe we just can't touch the sphere. Maybe there's no way to measure it. Whatever the method was, we measured it to be 21. Potential error of 0.05 centimeters in the measurement of the radius. That's the error. So we want to find out what the maximum error in the volume is going to be based upon that. All right, so let's write down what we know. First of all, we know volume of a sphere is 4/3 pi r cubed. We measured our radius to be 21 centimeters. Delta r in this case is what we're saying, okay, what's the measurement error? Well, according to this, the most that we could be off by our measurement, we estimate to be about plus or minus, we'll say plus or minus 0.05 centimeters, because we might have measured a little bit more, we might have measured a little bit less, but no more than 0.05 centimeters in either direction. Okay, so the error. This is where differentials come in. If we were to take the derivative of the volume, well, that's going to be dv over dr, because it's the derivative of volume with respect to the radius, since that's what we actually took the measurement. This is not dv over dt. It's not something changing over time. It's how is the volume changing with respect to how the radius is changing. So it's dv over dr, That's the left side. The right side, you take the derivative just by bringing, because r is in this case is the independent variable, you bring the 3 out to the front and multiply it by 4/3. That gives you 4 pi r squared because you reduce the power by 1. Again, no dr dt because it's not over time. It's just the volume with respect to the radius. So then if we want to solve this thing for a differential of v, what the approximation of the change in volume is for v, we're just going to multiply both sides by dr. So we're going to get 4 pi r squared dr. Okay, so dv in our case, well, let's see what we know. We know 4 pi, we know the radius that we measured was 21. So that's 21 squared. And our change, our dr, which is the same as delta r, like your x, they are the same, is plus or minus 0.05. And then we can actually go ahead and get a value for that. It's going to be a positive or negative if you plug all of that stuff in. 4 pi 21 squared times 0.05 plus or minus, you're going to get plus or minus 2.77, nope, that's 277, sorry, I read that wrong. 277.088 centimeters cubed or so. That seems like a pretty big error. 277 cubic centimeters, that seems like that could be off by quite a lot. Well, a better picture of the error is going to be what's called relative error, which is computed by dividing the error that we found in volume, dividing what we just found by the total volume. And that would be the total volume that we anticipated it to be based upon our measurement. So there's a lot of algebra that goes into this, but your delta V over V, that's what I just said, you're going to take what we just found to be the error, delta V, over the actual volume. But remember that delta V is approximately equal to dV. That's what we found here. This is the dV. That's what that is. That is dV. So we're basically just going to replace that and do dV divided by the volume. Okay, again, there's a bunch of mathematics that go into this. This was the dV. That's what we just found. This is the actual volume of a sphere, 4/3 pi r cubed. If you reduce all that, it reduces to this, which just makes it easier to plug stuff in if you really want to. Or we can just take the dV, the 277.088, and divide it by our volume. So I think that's the way I'm going to write it. It's I keep putting the decimal in the wrong space. 277.088 divided by the volume, which would be 4/3 pi times 21 cubed. And then when you plug all that stuff in your calculator, what you get out of it is 0.007143. That's what's known as the relative error. Okay, but that is not a percentage yet. So if we want to give the percentage error, remember, to give a percentage, you just multiply a decimal by 100. So the percentage error is going to be the relative error times 100%. So all we have to do is multiply our decimal 0.00713 by 100%, and we get the relative error to be 0.7143%. That does not seem so bad. A 0.7143 percentage error. Now that's not going to be good enough for a lot of things, because a lot of things are going to want your error to be much, much smaller, but that's not that big of an error if you make an error in measuring your radius by 0.05 centimeters at most. So there you go. We've talked about the differential, we've talked about the error, the relative error, and the percent error all in this last video. That's plenty enough. There you go.